Oh, there we go. Hi, everybody.
Excellent.
We've got our screen shared. We've got the program started, and you see that there are 4 of us here. And in this case, one of these things is not like the other 3. We have with us today. we have with us today, of course. We have Dave Holdorf and Rick Mayo. And off screen, we have John Messenbrink and Tim Ward from Mechanical Hub. And the rose among the thorns is Carol Fay. Hello, Carol.
Hi.
And Carol will be sharing with you all of the wisdom of her many years in the industry, understanding the fabulous mysteries of electricity. And she's going to tell us all the latest new developments and what's new in electricity, right? This stuff changes. I mean, it's constantly an evolving field.
Every day. Oh my goodness.
That's
yes.
right.
That's right.
But anyway, we've got
new
a
ways
fun.
to screw things up in a boiler room. Yes.
Right, there we go. We have a fun-filled evening for you for session 5 of TACO After Dark. And to kind of just get this thing rolling, I do want to toss it back to John and Tim. And if you guys, just because this has come up a few times, if you guys like to take a minute or so just to share with the crew what Mechanical Hub's all about.
Yeah, this is John. About 10 years ago, we started Mechanical Hub as an online resource for plumbing, heating, hydronics, mechanical contractors. So it's mechanical-hub.com is where you can find us. And since then, we've branched off into social media on Facebook, Instagram, LinkedIn, you name it. And we have a lot of fun doing it. I just posted a story about Dan Foley as our person of the year, which is pretty cool. And so, if you haven't seen it, take a look at it. I think you'll like it. There's a lot of information, fun stuff. And it's all about you guys. So yeah, thanks, John, for letting me bring that up.
Oh yeah, I mean, Mechanical Hub's just a terrific clearinghouse for information, something I try to check in on as often as possible to find out what's going on in my own industry. So really, if you guys are not followers of Mechanical Hub, it behooves you to do so. And you'll get to know the man, the myth, the legend that is Eric Awney, who never seems to show up here. But I guess when you get to be as big as Eric is, you just don't really hobnob with the little people, do you? You're hobnobbing with the big folks. So he doesn't really hang with us, I guess. That's all right. That's all right. Anyway, let's get this show started. As you may have guessed, due to the Quint's shark fishing T-shirt, the movie of the night is Jaws, one of the great movies of the 70s, Jaws. And I just want to get a couple things on the table for us. Navigating the control panel for you first timers, okay? If you take a look at your control panel, you see a little hand. If you see that, see this this whole control panel. If you click on that orange arrow that's pointing to the left, then you'll expand the whole panel and you'll get to see what other stuff is there. Ultimately, what you want to do is you want to get to this part right here. This is where you're going to type in your questions, okay? And the presenter, co-presenters, and panelists will see that. So if you guys could do all that for me, a lot of you already know how to do that, but if you want to just throw in a hi, hello, how are you? There we go. There we go. Everybody's out there. Okay, excellent, excellent, excellent. Good, good, good. Everybody's chiming in. So we are all set. All systems are go, and we are ready to get this party started. And there's my man Quint, one of the great characters in all of the 70s right there. But anyway, tonight we're going to be talking about, before we get to Carol and start talking about electricity, we're just going to talk about boilers and what sizing a boiler for this project that we've been working on, and then a couple of fundamentals of boiler piping, and then talk a little bit about how this all interacts with an indirect, because we've got a really small load here in this house. If you remember going back, our total load was 30,577 BTUs for this house in Norwich, Connecticut. If you've got a load of 30,577 BTUs, Dave and Rick, I'm going to ask you guys, what's the challenge here? When you're trying to pick a boiler, what's the biggest challenge facing you when you have a load of 30,577?
Getting one that small.
Yeah, because you just don't make them, right? You just don't make them. And if you do find one that small, and ModCon boilers help us a little bit because of turn down ratios. If you do find one that small, what's the other challenge? Is making domestic hot water, whether it's in a combi unit or whether you have an indirect. So there's all kinds of challenges here when we're talking about a boiler that small. So we're going to look at some options here for boilers that small. We picked a couple of different boilers to consider from NTI and from Weil-McLain. So we're going to take a look first at just an NTI heat-only boiler, the NTI TX51. And I chose that one because, as you can see here, it has a net AHR output of 45,000. Now, net AHRI, for you old timers out there, you might be familiar with the term net IBR. Well, net AHRI is the exact same thing, but with a different wrapping on it. AHRI bought IBR, so IBR really is no more, it's AHRI. So the net AHRI output is your net IBR output. So 45,000, that's pretty doggone close, okay? From an input standpoint, it's 7.1 to 57 MBH. That's about an 8-to-1 turn down ratio. But at that even at that low firing rate, that boiler's still going to be kind of on the big side for this project. It's not bad, but it's still going to be kind of on the big side. When we get into talking about boiler piping later on today and also in upcoming weeks, we'll be talking about how in something like this, a buffer tank really starts to become really important when you want to try and maintain the peak efficiency of that boiler, operationally speaking, not necessarily just combustion efficiency. Now, better still, we could take another look at the NTI TRX 085. Now, that's a 9.4 to 85 MBH with an 11-to-1 turn down ratio. The DOE output is 79,000. The net AHRI is 69,000. If we had to use this to make domestic hot water, this might be a possibility here. That would be a benefit to us. With that 11-to-1 turn down ratio, that still helps us with the smaller load, but we'll still probably want to look at a buffer tank in this application, I would think. If we wanted to go with a combi unit, we'd be looking at the TRX 110C. Now that's one that'll do a boiler that'll do both domestic hot water and your heating system water in sort of an instantaneous or tankless type of situation. Now we're talking 11.2 to 106 MBH, again, still an 11-to-1 turn down ratio. Now your domestic hot water continuous flow is 2.7 GPM at a 77-degree rise. So if you got 50-degree water coming in, that's 127-degree water coming out, which in most cases, since you're not storing, that's probably going to be okay. At 2.7 gallons per minute, we're not dealing with 3 showers and a hot tub all at the same time. Okay, you've got some limitations here, but in most normal applications, we probably should be okay. We probably should be okay. And Jason Mangos, I saw you out there. If you're out there, or Wheels, if you're out there too, if you want to chime in on that output and what that means, that would be awesome. That way we give our guys a little bit more info on what that really means. So, so these are some NTI options for you. And again, remember, 30,000 BTU max. That's on the coldest day of the year for heat. So again, any one of these boilers we've picked are going to be too big. We're not going to have an 11-to-1 turn down ratio if we use either one of these for heating. We're maybe going to have a 3-to-1 or 4-to-1 turn down ratio. Okay, 9.4 MBH. It's probably going to be about a 3-to-1 turn down ratio because it's just a small load. But that's better than a 2-to-1. Okay, the previous model might work out a little bit better on that end. If we were to look at a Weil-McLain option, I'm going to look at a ModCon and just a standard efficiency model. We're taking a look at this one, the WM97 plus 70CT. There's a lot of syllables there to digest. We've got it's a small boiler, again, 14 to 70 MBH. It's a 5-to-1 turn down ratio. Its DOE output is 65,000. They don't list an AHRI output for that one. So it's 65,000. Boiler's still twice as big as it needs to be. All right, it's still twice as big as it needs to be. So we're not going to have a 5-to-1 turn down ratio. In this case, it's probably going to be about a 2.5-to-1. That's basically what we have. The load's so low, that's the reality of the situation. Now, if we were to look at a standard efficiency boiler, we got a little bit something to look at here. The CGI 25. Now, that's a 50,000 MBH input. The DOE output's 42,000. The AHRI is 37,000. Now, if we're not, over the moon about putting in a ModCon boiler, there's something to be said about putting in this small of a boiler that's going to be more accurately sized for the application. Now, again, 42,000 BTUs gives us some serious limitations in making domestic hot water if we're going to use this for an indirect. If we're going to have a separate water heater, hey, we don't, this might be one of the only instances where it might make sense to use a separate water heater. I don't know. That's one of those open questions that you always kind of wonder about when you're talking about boiler sizing. If we've got such a small boiler load, do we want to put in a big honking boiler just for domestic hot water and then have it run relatively inefficiently for the heating system? Or do we want to set up a boiler that's sized for the heating system and then a separate burner and set up for your domestic? I don't know. I'll throw that open to Dave and Rick. What does your experience tell you?
As far as cycling the piece of equipment, when we don't have the turn down ratio, we have more cycling. When we have more cycling, when we have more wear and tear, we've gone through this before. The other thing that's actually come up recently is there's plenty of studies that talk about when you cycle a piece of equipment, how much more, I'll just generally use the term, pollution the boiler creates. Okay, the boiler doesn't have the efficiencies when it lights and when it extinguishes, and those two times when the boiler does that, it kind of spits out the most pollution, and the more it cycles, the more that it contributes. Now, again, I only is saying that because I just got off the Hot Water Forum class today, and they spent a bunch of time talking about that. So anything we can do to get the piece of equipment to cycle the least is a good thing.
Very good, very good. I get a couple of comments out there from folks about different ideas here. Bill Chanel says even a 50,000 BTU boiler tied to a 40 or 50 gallon indirect gives you more recovery than a standard 40 gallon water heater. Perhaps, yeah. Again, we're going to discuss recovery in a minute here and show you the math behind recovery. So 50,000 BTU boiler is going to give you a little bit of recovery, but is it enough? And you may, I think where you were going with this, you may have to find that you need a larger tank. You can certainly get around that with a much larger storage tank. So you're storing more water for those sudden dumps. If it's 2 showers and you never run them at the same time, well, then we've got different choices here. All right, let's take a look at some indirects here now as well. So to figure recovery, this is your formula to figure the recovery that you can get out of a boiler. It's about the BTUs you have available at the boiler to make domestic hot water. So to figure recovery, you simply divide that boiler's DOE output by 45,000. Where does 45,000 come from? Well, we multiply 8.33, which is the weight of 1 gallon of water, times 60, the number of minutes in an hour, times 90. That's the DOE recommended temperature rise. That's 50 up to 140. Now understand 50 up to 140 is going to give us a boatload of room here, okay? It's going to give us a boatload of room because we're not going to take a bath in 140 degree water, not twice anyway. And we're not always going to be bringing in 50 degree water. That's considered a worst case scenario, unless you're in a place like Alaska where the water comes out of the ground frozen, basically. So you've got to make those different adjustments. But this is kind of a good rule to work with. So it's the DOE output of the boiler divided by 45,000. So let's take a look at that NTI TRX 085. Okay, so that DOE output at max fire was 79,000 BTUs. Divide that by 45,000, that gives us 1.75 gallons per minute worth of recovery. That's what it can do. Doesn't matter anything else. That's all the BTUs it has available. Okay, that's all it can do. Now 1.75 gallons per minute times 60 minutes, that gives us an overall 1 hour recovery of 105 gallons, okay, per hour. So we can recover at a rate of 105 gallons per hour. Now, if we were to install a 45 gallon tank, you figure 45 gallon tanks, any tank really, about 75% of that is usable as a dump at that temperature, okay, at the peak temperature, because of 2 things. Number one, you've got a lot of space taken up in that water, in that heater by the coil, by the indirect coil. And in addition, when you take hot water out, you're putting cold water in, and that just draws the tank down. So if we put that 34 gallons in with that 105 gallons worth of recovery, that gives us our first hour rating. That's how first hour ratings come by. Our first hour rating for this tank for a 45-gallon tank with this water heater, or with this boiler rather, that's 139 gallons for the first hour, or we are now recovering at a rate of 2.2 gallons per minute at 140-degree water. Now, is that going to be enough? Well, we got to do a little bit of math on the flip side to figure that out. But in a lot of cases, it probably will be. With your shower, you're not taking a bath at 140 degrees. You're tempering it down to 106, 107, or whatever it is you take a shower in. You've got your dishwasher's going to be running at a certain temperature and all these other things. And you may even put a tempering valve at the tank itself to extend that capability. So there's a lot of places to play here to see if you're going to have enough. But this at least gives you a starting point so you know what I realistically have to deal with this smaller boiler. Now let's take another step forward with this, and let's look at the reason I chose the WM97 plus 70 is because you have this optional tank that goes with it. It comes with the Aqualogic. It just has a tank that goes with it. It's an 18-gallon tank, all right, that kind of connects right to the boiler. 18 gallons, that's 13 and a half gallons of standby, 13 and a half gallons of usable water. All right, at 65,000 BTUs, which is the DOE rating, divided by 45,000, that gives us 1.44 gallons per minute worth of recovery. All right, we divide that out or multiply that out by 60 minutes. That's 86 and a half gallons per hour plus 13 and a half gallons usable. Now we have 100 first hour gallons, or roughly 1.67 gallons per minute at 140 degrees. Again, we have to figure out A, how long, B, how hot, and C, what's the flow rate at the most important fixture. All right, again, if it's the shower, if this is going into a house with a 6-person shower and you got nozzles coming at you at 14 different directions, they're a heck of a lot of fun, but it's not going to be fun for very long, okay? You got about 3, maybe 4 minutes and then you're done, okay? So you always got to make sure, because you don't want to be on the other end of that phone call, I'll tell you what. So I told you, this thing goes sideways in a hurry sometimes. So this is the math, basically. This is the math behind that one. All righty. So a couple quick questions here. Our comments. Let's see what we have here. Boom, 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 boom. In my US boiler Aspen digitally, I can set the max BTU load on heating, and then my 10-to-1 ratio moves within that parameter. Well, that's a pretty cool boiler. That's really neat with that control. Let's see what else.
That's that Sage control that we also make on the Burnham boiler.
Oh, very good, very good.
Yeah,
right.
So they get a pretty cool options on what us and US Boiler was able to do when we designed that Sage controller that ties into their system too. It really gains a tremendous amount of efficiency into the system.
Very good, very good. And Bill says with the water temperatures we can use for heating, we really do need to condense. Yeah, again, if we're designing around a low temperature system, absolutely. Now, if we got a multi-temperature, multi-load system, we got to make some decisions. And there's always that option of using a high temperature boiler and then mixing down for the lower temperature stuff. If you've got 2 different temperatures, there's always that possibility. I mean, the industry is moving towards ModCon, and that's just the way it is, because it's the better choice. On a case-by-case basis, you do have to take a little bit of a different look at it. And something like this, I'm not entirely sure which way I would go, to be honest with you. I don't know. What do you guys think? If this was your house, Dave and Rick, this was your place, which way would you go for a boiler?
I'm gonna kiss it. Keep it simple, stupid. Oh yeah, yeah. I can't be the only guy that knows what's going on. If somebody else comes walking into that boiler room and sees what the heck's going on here, so you lose a little bit of the efficiency on one side. You try the best you can, but I'm still looking at the keeping it simple in my boiler room.
Very good. How about you, Rick?
Yeah, I'd stay with what I was reading a question when you were doing that, but I think what you meant was I would keep a single boiler, not use a boiler and a water heater. I would let the boiler do an indirect, so on and so forth. Now,
Okay.
if I answered that wrong, remind me what the question was.
Well, would you go, in this case, would you go with a standard efficiency boiler at 30,000 BTUs or a ModCon? And it sounds like you'd go with a ModCon or something large enough to handle the domestic hot water, which kind of changes the discussion a little bit.
Yes.
Gotcha. Okay. Very good. Excellent. Excellent. All right. I'm in the middle. I'd have to flip a coin, you know, see which way I'd go. I'm really not sure. All right. Let's take a look real quick at some boiler piping fundamentals before we turn it over to Carol. Again, ModCon boilers, just looking at your moose antler piping. And we're going to get into this next week a little bit deeper on the specifics of piping up a ModCon boiler and sizing the boiler pump as well as the system pumps. We're going to get into that in detail next week. The air separator, I just want a couple of little things I want to show you. That air separator expansion tank automatic fill kind of setup is kind of sitting right there on the supply side. Any guesses on why we put the air separator on the supply? That's where it should go, but why would you put the air separator on the supply? And if you know that answer, just type it on in, because I think I know why. And while we're at it, the mag dirt separator, which you see over here, the mag dirt separator is always on the return. Why is the mag dirt separator always on the return? Why is it supposed to be on the return? Okay. Couple things. When we're talking about putting the air separator on the supply, a couple of you guys got it already. Very good. That's where the water's the hottest. And one of those laws, I forget, is it Boyle's law or Henry's law? I can never keep them straight. One of those laws says that the hotter the water, the higher the temperature of the water, the less capable that water is of holding dissolved gases in solution. Just think about boiling water for a second, okay? The dissolved gases in the water start to turn into bubbles, you know, and they bubble right out of the way, all right? Is that Boyle's law, Wheels? I can never keep those two straight. So if that's in fact the case, the hotter the water, the less capable that water is of holding dissolved gases in solution, meaning those dissolved gases want to tend towards bubbleness, all right? If that's in fact the case, well, why not put the air letter outer in the position on the system where the air wants to get out the mostest, right? Where the water's the hottest. Why fight nature? The air wants to get out. Okay, we don't want it in the club. Let's let it go. All right, it wants to get out. Let's let it out. All right, so that's why the air separator always goes on the supply where the water is the hottest. The mag dirt separator on the return, on that case, let's protect the boiler, because there's all kinds of crud out there in the system potentially coming back into the boiler. Those ModCon boilers, they got little teeny weeny passageways that can get plugged up, and that's just the death knell for a boiler. As we learned a couple of weeks ago with Patrick, yes, we treat the boiler water, but we also put a dirt mag separator on the return side to catch all that stuff to keep it out of that boiler in the first place. So
there's also another good reason for the air separator on the supply side, and based on this piping diagram where we're pumping away, it's also the lowest pressure in the system right there too. So when we also have that lower pressure in the system, before we get the pressure differential coming out of that circulator, then we're going to also help get the air out. Because how many people here enjoy purging? Not many. Nobody. I don't care who you are out there.
Those are the worst.
Yep. So let the air separator do its job. You put it in the right spot, it's going to do its job.
Bingo. There you go. Very good. And lastly, our fill pressure is 12 psi. Our fill pressure is 12 psi. And again, why 12 psi? That's always been a good question. What's so special about 12? I mean, if you ever saw, what was that movie? Murder on the Orient Express. They were always worried about 12. Where does 12 come from? Not Perot. Is it Perot? Hercule Poirot. I always think of H. Ross Perot, but that's a different Perot. Hercule Poirot figured out the 12 and the, go see the movie. Just go see the movie, all right? But why 12 psi? Well, again, we learned this day one of plumbing school. 1 psi is equal to 2.31 feet of head pressure. A column of water 28 inches high, a column of water 28 inches high or 2.31 feet high will have a gauge pressure at the bottom of 1 psi. All right, so 1 psi is equal to 2.31 feet. All right, if we fill a system to 12 psi, 12 psi times 2.31 feet per psi, the psi's cancel each other out, and that gives us 27.72 feet. That's the pressure needed to lift the column of water 27.72 feet in the air, and that, friends, is enough pressure to keep the radiation filled and pressurized on the radiation level of the upper levels of a normal residential structure with a little bit left over. Okay, so that's why 12. That's why expansion tanks come charged to 12. That's why pressure reducing valves are preset to 12 PSI. That's the whole 12 PSI magic right there. If you have a taller structure, maybe you need to fill to 15 or whatever. Again, a little bit of math. And whatever you do to the pressure reducing valve to change the pressure on the pressure reducing valve for the system, you must also do to the air side of the expansion tank. And the only way to change the pressure on the air side of the expansion tank is to do it when there's no water on the water side. So you have to do it when there's no pressure on the water side. So that's always a fun little game to play. Just before we go over to Carol or get into our trivia question, go over to Carol. Last thing is about the boiler trim kit, something new that Taco has been offering for the past year or so. Basically it's an expansion tank, air separator, and automatic fill, backflow preventer, all in one box, in one kit. Now it doesn't come assembled like you see here. It comes with everything's in one box, but you have to put it together. But it does come with the nipples, the fittings, and that little isolation drain valve that you see there with the yellow handles. It all comes together with the whole thing in one box, just for convenience sake. Okay, and you can get the deluxe package like we show here with the 4900 air separator and the Taco 3450 combi valve. Now this is a one-piece backflow preventer and automatic fill valve in one, so it's just one unit. Okay, it's just one unit. And the cool thing about that is if you take a look at that little green extension piece, there's an indicator here for pressure. It tells you what the pressure has been set at. It's not a pressure gauge, but at least it tells you where it's been set. I've never seen that on any other automatic fill valve. Most of them have that little set screw or something on the top where you got to kind of adjust it and kind of guess and hope where you are. Okay, but this one does not have that. This one, you can adjust it. By turning the green knob, you can adjust it and you'll see where the pressure is set, which is terrific. Now, does it go, as a question here, does it go into a fast fill capabilities? Absolutely. That button, and this is where it gets really cool, that button on the end of the green extension, you press that in and it goes into fast fill and it stays in fast fill. And here's the cool thing, with a standard fast fill valve, you got to lift a valve, right? You got like lift a little lever or handle or something to put it into fast fill. And then you got to go over and purge, right? You got your hose and you're opening up closing a valve, opening up a drain, and then blowing out the air. And when all the air is out and you got a nice steady stream of water, then you go back, you close the drain, you open up the valve, and then you got to run back to the fast fill valve and get it out of fast fill before you blow the relief valve. I want honest answers here. How many of you have not got back in time at least once in your career and then have had the 30-pound relief valve blow? If you say no, I know you're lying. It's pretty much everybody in there's done that, right? Well, with this, if you press it, it stays in fast fill until you hit the preset pressure of 12 PSI. When it hits 12 PSI, bang, it comes out of fast fill automatically. So it kind of saves you from that embarrassing, oh crap, what am I going to do with all this water thing? So that's a kind of a neat feature, neat function to that 3450 combi valve. And it's a nice little compact one-piece setup. And as you see, it's sweat, union, it's press. You have it in a lot of different options. So with that, just real quickly show you, again, piping with an indirect. Again, we're going to go over this probably in a little more detail next week. And here we have boiler piping with a hydraulic separator. Now, before I turn it over to Carol, we have our Taco movie trivia question of the night regarding Jaws, regarding the movie Jaws. Now, Jaws was directed by Steven Spielberg, came out in 1975, the summer horror flick of the year. Spielberg's shark, the shark was the star of the movie, right? And it was a landmark in what they call, I'm going to try to pronounce this the first time out of the box, animatronics. Very good, animatronics. The shark even had a name. The shark had a name. What was the shark's name? What was the shark's name? Type that into the answer to your question section. And everybody who's got the name right, we'll be putting you into a little spinorama for next week and pick a winner, which we're going to do this week for last week's question once we're done here. But that is it. What is the shark's name? What was the mechanical shark's name? All righty. With that, time has come to hand this show over to Carol Fay. Carol, are you ready?
I am ready.
Are you ready? All right,
Yeah.
I am going to make you
Great to
the
go
presenter.
down Boiler Lane again. Wow.
All right, you are now the
Uh,
presenter.
Okay. Can you see me talking, or do I need to show my screen?
You're going to need to share your screen. We can see we have the
Okay.
we have the webcams up, but we're going to need to see your screen.
Okay. Wait a minute. Gotta get the slideshow up. Someday we'll all be very good at this. Well, you're already very good at this. I'm not very good at this yet.
Well, we've been practicing a lot.
You
There we
have
go.
almost 10 years, did you say?
We've been
Almost
doing
9 years?
webinars almost 10 years now, I think.
That's a hell of a lot of practice.
And we've been doing 10 years. We've done 10 years worth of webinars the last few months.
Oh, yes. Okay. That's
Didn't say the first 8 were any good though.
Yeah.
Well, I don't have to talk about everything. Oh, well, John told me that there have been some requests to go over how to use a meter. And that's what we're going to do. The slide I'm showing right here is my books. And they've been around for a while. They are made for people who like more pictures than words, and who like to have only what you need to know and nothing else. Added on to that are now an online interactive electricity training. So if you have students, employees who need to be introduced to basic electricity, you could look online and get that interactive thing where they can use their iPad or their computer mouse to actually wire circuits and then get immediate feedback about you did it right, dude, or try something else. Okay, so moving on. Some of you remember the piggy. The piggy is still alive and well. I showed this just briefly to get reference to. We always have to think with meters about what it is we're measuring across. Are we measuring a switch, or are we measuring a power supply, or are we measuring a load? Because what we expect is different. A meter, this is all review stuff for most of you probably. A multimeter measure voltage, amperage, resistance. Resistance is the same as continuity, though sometimes it's shown different on a meter. And you can set it for AC electricity, alternating current, or direct current. That's batteries mostly. When we're using a meter for controls, we are looking at AC voltage and AC resistance. The rest of those possible functions we're not going to use. We used to use the amperage back when thermostats had an anticipator, but now that thermostats are digital, we don't need to do that anymore. Meter math. This slide answers a lot of questions about what the heck is going on with a meter and why is my meter always broke. A meter is a subtraction machine. So picture your two leads, your red one and your black one. What the meter display is going to show you is the difference between the voltage that those two leads or probes measure. So if you have 24 volts on one side of, let's say, a switch, that's one terminal, and 0 volts on the other, the meter is going to show you 24 volts because the meter is doing simple math. 24 volts minus 0 volts is 24 volts. People often think that the meter should be showing 0 because the switch is open. It doesn't work that way. On the flip side, if you have a closed switch, for example, the meter is going to sense 24 volts on both sides or both terminals of that switch. 24 volts minus 24 volts is 0 volts. If the 0, 0 happens, of course you have 0, and the same thing holds for 120 volts. When you have questions, go ahead and put them in, and then John and I have an agreement. I'll let him interrupt me for once, and I'll answer the question or say, ha, beats me. Okay, here we have a meter with a probe on one side of the switch and another probe on the other side of the switch. Is that switch an open switch or a closed switch? Well, it is an open switch. So what we would expect if the meter is telling us that yes, we have an open switch, is that the meter would show 24 volts because a meter is a subtraction machine. It subtracts 0 volts from 24 volts and says, aha, the answer to that simple problem is 24 volts. When you have a difference of voltage on the two sides of the switch, that means that the switch is open. If the switch were closed, it would be a direct path for electricity to go across the whole thing. And so this would have the same voltage on both sides of it. The subtraction machine meter would say, 24 volts on this side and 24 volts on this side. The answer to that simple problem is 0, so the switch is closed. If you think about a light switch, well, you have the position of the switch telling you up is open or closed and down is open or on and off. But for something like, say, a limit switch or an end switch, you don't know by its position, end switch and a valve, you don't know by its position whether it's open or closed, so you might want to find out. And this would be a way to do it. Another thing the switch can, or this can tell you is your switch good or bad? So if you know the switch is supposed to be, let's say, closed, and your meter says, the answer to that math problem is 24 volts, then that tells you your switch is open. Here is my little drawing of electricity guys. So a lot of classes will talk about electrons having to do with the electricity, and are electrons this way or that way? It doesn't matter. What really matters for what we do anyway. What we need to know is there a pile of electricity guys on one side of the switch and not on the other? So the meter will tell us. If the switch, this is symbol for a switch, is open, there's the opening. If the switch is open, all the little electricity guys are piled up on one side. So the meter is going to sense, let's say, 24 volts worth of them on this side and none on the other side. So the answer is going to be 24, and that means the switch is open. We doing okay? John, we doing okay?
We are rocking and rolling.
We're rocking and rolling. All right.
Guys, any questions, just feel free to chime on in and write them into the question section.
Yeah. Okay, that was a switch. And the meter setting on that was volts. So when you set your meter, you have a V symbol, V for volt. And the rule for what you set the meter on, you have several choices usually, is whatever setting, the lowest setting that is going to be bigger than what you possibly expect in the circuit. So if you don't know, heaven forbid, if your circuit is 120 volts or 600 volts, then you would choose the 600 volt setting. But if you know you have a 24 volt circuit, then you would choose the lower setting. It's just so as you get a more exact reading. Now, let's move on to another part of a circuit, power supply. A power supply is where electricity comes into the circuit. You may know it, we're switching to 120 volts here. It doesn't matter what the voltage, whether we're talking 120 or 24, it's going to be the same rules. L1, L2, that stuff, we don't need to fuss with that right now. The arrows are pointing out to whatever the real power supply is. So if you're plugged into a panel in the building, then the panel is out here. If your power supply is a 24 volt transformer, then your power supply is right there. You got to put the power supply in there. Whoops, I went backwards. Let's see if I can get it to go backwards. Nope. I forget which way to go backwards. Well, we won't do that. We'll use this one right here. Anybody know on PowerPoint how to go backwards? Type it in, John.
I'd say the up arrow key or the down arrow key.
Should I try that? Ah, yes, thank you.
There you go.
Yes, you did it. Okay, we're going to, what we expect here because of L1 and L2 and what the power, let's say the electric, this is 120 volt line voltage, and this is what the utility gives us. So L1 is going to be 120 volts. L2 should be 0 volts. It's neutral. We don't have to worry about that. We just know that they should be different. That means that the meter is going to show us an actual number, and that means it should show us the voltage that's coming in on L1. So we put our meter across L1 and L2, and lo and behold, we see across the meter 119 volts. We hardly ever see 120. The utility gets to do whatever it wants. We all know that. So it'll be whatever voltage there is today. It will often be higher in the off season for air conditioning and heating because there's less load. It'll often be a higher number in the evening than it is during the day when there's lots of electric or industrial and commercial use. But anyway, something around 120. Mostly what this is good for in controls work is, do you have voltage going into the circuit? So back when I used to get troubleshooting calls, especially on Friday night, it seemed, the question will be, why won't my boiler run? You're my last resort, Carol. And I said, oh, good. Thanks a lot. It's Friday night and I'm your last resort. I am charmed. But often the big problem is we don't have electricity going into a circuit. So an easy thing to do is get out that old meter and see if you actually do have voltage coming in. And that is measure across L1 and L2. What do you have? Same thing for across a load. Let's review now what these parts are. So staying with 120 volts, let's say that our power supply is 120 volts coming in from the supply panel. And there's our switch. That's a symbol for a closed switch. Here's our load. Let's have our load be a light bulb. We can measure across the light bulb. And these terminals, these really should be clicking in right about there. So you got one of your black probe or your red probe there, and you got the other one on the other side. And what do you see? You know that there's electricity going through that circuit because the light's on and your switch is closed and you have power into the circuit. But remember that a meter is just a subtraction machine. So if you have 120 volts coming in here and 0 volts coming out there, that means the load ate up all the electricity. And that's what we expect. Okay, let's move on to where are we now? We have a little review here. I want to go back to, okay, meter math, review. 24 volts on one side of a switch or a power supply, and 0 volts on the other side is going to tell us a different message depending on whether it's a power supply or a switch. If it's a power supply, it tells us, yes, we have voltage into the circuit. We got some. If it's a switch, it tells us in this case that the switch is open because the voltage is different on the two sides. Let's go back and review that. Almost right there. So open switch, this is the hardest part right here. 24 volts, the electricity, let's switch back to, well, it could be a transformer, 24 volts or 120 volts. Doesn't matter what the meter is going to be telling us about the switch. So we have 24 volts going that far. If the switch is open, the 24 volts can't go any farther. The switch is open, it's turned off. 0 volts on the other side, and that tells us the switch is open if we see 24 volts. If we see 0 volts, the switch is closed. And again, that's useful for those many switches in our world that you can't see whether they're open or closed. All right, moving on to, there is a method of diagnosing a circuit with a meter called leapfrog or hopscotch. It has a bunch of different names. And it means you go around the circuit with one probe of your meter. You keep the other probe in a stationary position. So this probe right here, we're going to keep it right here. It doesn't matter which side of the power supply you're on. In this case, the power supply is a transformer, but again, the effect in the circuit is the same. I'm going to keep that one right there. It's not going to move. This one, we're going to move around the circuit. If we have one probe on each side of the power supply, we expect it to show us the voltage coming into the circuit, because this side has none, this side has some, and the difference between none and some is like 24 volts or roughly 120 volts. Then we're going to move that probe, the one that we're moving, let's make it the red one, doesn't matter, it could be either one, to there. Now we're going to see 24 volts because there is no voltage here, that's your L2 neutral, and there is some voltage there because it's coming in and it gets to there. I'm going to move this probe to the other side of the switch, and if it's a closed switch, you're going to see 24 volts on the meter. So that tells us, that switch is closed. Good, that's what I wanted. This is also for a situation where you can't really tell if the load is energized or not. If that were a light bulb, here is the load, you would know, of course, because the light bulb is turned on. But in this case, it's a valve, and you can't always tell by looking, in fact, you often can't, whether the valve is energized or not. Now, we're going to move on. Here's the neutral probe, or the probe on the neutral side of the power supply. And it's going to move now to here. Since the switch is closed, we are still going to see voltage because the difference between neutral and the electricity got through the circuit all the way to there. There's 24 volts there. There's none here. The difference is 24. Here's where it gets really fun. When we move that probe over to the other side of the load, the purpose of a load is to eat up every last bit of the electricity that went into it. Every last bit, none left over. That's the rule. Even if it has to burn itself up, this is the load, or a coil, it will use up all the electricity. In this case, it didn't use it all up. It powered the load, and there is no electricity that comes out of that load, ever. And on that side, there is 0 volts came out, and there were 0 volts on the neutral side, and we have 0 volts on the meter. So that's hopscotch, or leapfrog method of troubleshooting. Okay, now we're going to change our meter setting from voltage, that's the letter V for volts, to something else. What we're going to change it to is, on your meter, you will have possibly an upside down horseshoe called an omega. The reason that omega is used is because the measurement, kind of like we had voltage before in V, the measurement is in ohms. And if we use an O for ohms, like we used a V for voltage, it would be It would look like a 0. That would be confusing. And so instead, whoever made this stuff up, I guess it was Mr. Ohm, decided to use the Greek letter for O, which is an ohmic, upside down. And you have probably a setting on your meter for ohms. And that also will measure what is called continuity. I'll explain that in a moment and what it's good for. Or you may have on your meter a symbol, which is like a number of parentheses together, 3 or 4 of them, one bigger than another, and that's a symbol for it makes sound. So so often when a person takes the meter out, they turn it on, click, 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 set it to something, put the 2 probes together, the black and the red, and that meter goes screech. And if you have a class and a bunch of meters, then you get what I call the meter choir, which is a lot of screeching. And I say, stop that, that's awful. They don't. What the meter sound says is the same thing that the ohms would tell us, is that there is continuity or a pathway for electricity to get through between one terminal of the meter to the other. So let's say we're going to measure, let's do continuity on let's do a transformer. Let's say if we want to know if is primary, let's not do that. Let's do a light bulb. We want to know without turning it on, plugging it in, is this light bulb good or bad? And shaking it didn't convince us one way or the other. So you would put 1 meter probe on the tip of the light bulb and the other one on that metal side. You'd have it set on sound or continuity. And if it makes a sound, that means there is a pathway for electricity to get from one probe through the load, through that little wire inside of the light bulb, back to the meter. And that means your load is good. If you don't have the sound, you could use the ohm setting, and instead of a sound, you'll get some reading on your meter. It doesn't matter what the reading is. If you get a reading, it means there's a path for electricity and it's good. In basic controls, we're never concerned about what the ohm reading is. We're just, do we have some? Yes, then there is a pathway through that load. So what happens is for power supplies with the circuit, the meter has, mine anyway, has a 9-volt battery in it. So that 9-volt battery in the meter sends out 9 volts. And it goes out 1 probe. It goes through the load. If it makes it all the way through the load to the other meter probe, then it makes a sound. And that confirms that the load has a pathway all the way through it for electricity and the load is good. If you get no sound, then that means there isn't a pathway and the load is bad. You can also use it to test switches. So we have 2 ways to test switches. One of them we already saw, which was with voltage. Let's go back to that. With voltage, and we can measure, is there voltage here, and if there is voltage, it means the switch is closed, or yeah, it's a closed switch. With continuity, what we're doing is measuring, is there a path for electricity to go through the switch? So if you put your probe on one terminal of the switch, and you put your probe on the other terminal of the switch, and you have it, your meter set for continuity or ohms, then if the switch is closed, you get a beep or an ohms reading. If the switch is open, you don't get anything. And that can tell you whether the switch is open or closed. John, do we have questions?
You must have knocked it out of the park, Carol, because there's very few. There's one regarding Christmas lights. If you can put as many Christmas lights in series until the voltage drop of each added up leaves the last light with its minimum required voltage.
Yeah, what would happen if you, This is a design thing for the manufacturer that they put the right number on there.
Right.
Let's look at it another way. We can get back to this part of it. In the old-fashioned Christmas lights, they aren't made that way anymore, but I think we all have some and they've frustrated the hell out of us.
Oh, yes.
If you have one light that's burned out, that's an opening in the whole path for electricity for a series circuit, which is what those old-fashioned lights are. That means the electricity has to go through every last one of those bulbs before it can get back to the power supply. And if one of those bulbs is burned out, that means there's an opening in the bulb, then electricity can't get all the way around the circuit and nothing will light up.
And they always give you those little replacement bulbs, but you have no idea which one is blown. So beautiful planned obsolescence on their part. I think that's brilliant.
Well, yeah, and it's just fine if there's only one burned out. I mean, I've been there. You find that you just replace each of them one by one by one by, and eventually you get there. Even if it's the last one you found it. But if there are two, the chances of finding the right two are damn slim. Now let me ask you this. What looks like a similar situation is the light bulbs above many bathroom vanities, where there's not just one light, there's 3, 4, 5, 6 light bulbs above the vanity. You know what I'm talking about?
Mm-hmm.
And one of those bulbs can be burned out. In fact, it's kind of an insurance policy. You don't have to change the lights out, replace any light bulbs until the last one burned out, because you always have one left.
Yeah.
And you wish you hadn't, because then the bathroom's dark. You know, oh, God, I wish I'd replaced this when there was still one. Are those wired the same as Christmas tree lights? It looks like they are because they're all in a row, but they aren't at all.
Right.
In that case, each of those light bulbs has its own circuit. So there's a power supply, there's the switch, the wall switch, probably through that light bulb and back to power supply. And then there's a new circuit, believe it or not, from the power supply through the same switch to the next light bulb and back to power supply. Each one gets its own. What else you got?
Well, let's see. Here's one from Ryan Barowie. Question about testing thermodiscs that are normally open. Would a continuity test still work? Because theoretically, there is nothing to heat the element to allow that metal to and make internal contact. A thermodisc.
A thermodisc, I have never worked with a thermodisc, but from that description right there in the question, it seems like, and if anybody knows better, be sure to chime in and say so. It seems like if there is no beep for continuity, then that means the switch is open. And then if you heat it up, I don't know, can you put a candle under it or something?
Yeah.
And that closes the switch, and then you do get the sound for continuity. I'm making this up. How am I doing?
Well, continuity is basically open or closed. How it gets there is a different discussion, I guess. But yeah, if it's.
Oh, yeah. It's just telling you, do I have a path? Does this electricity have a path to get back to where it started? That's all it's about.
The questions are rolling in here. Yeah, Ryan says you can put a candle, but you'll damage it. So probably not a good idea, but.
Burn up.
Maybe you could just breathe on it. Say again?
Does that work, Ryan? Can you just breathe on it heavily?
Well, that you need a lot of heat. If you have two controllers, and each one will supply 120 volts to an oil burner motor, will there be harm if both controllers send 124 volts to the motor? Will the voltage double, or is it a parallel circuit?
It should be a parallel circuit that has only the load the load has only one way through it. The electricity can go through either switch, but either way, there is only one pathway for electricity to go through.
Okay, very good.
So what this gives you is this switch can turn on, or the other switch can turn on and it'll work, or you can turn on both but the effect is the same on the load.
Very good. Kind of like a circulator with zone valves. Well,
Yeah.
does it, all right. Okay, here's another question. The load doesn't always eat all the electricity, right? Depends on the voltage drop on each voltage drop each load causes? This one asked Mark Sheen.
No, the thing is, the load eats all the electricity, period. The thing is, the load has to be designed so that it can deal with all of the electricity. If the load's too small for all of the electricity, like say, for example, if we try to put 120 volts through a 24-volt zone valve motor, where the rest of the electricity goes, get ready for this, besides the 24 volts, the rest of it goes to heat and light and maybe sound when it goes pop.
Which is never a good thing.
I don't know if smell is part of that transference of voltage into some other form of energy, but there is that distinctive smell when you say,
Right.
oh, I don't have another one.
I remember years ago on a job site, someone set the generator to 220 and then plugged in his Sawzall, which is a 120 volt tool. And for a moment, his first reaction was, wow, this tool is supercharged.
Yeah.
It didn't last long, but it was an immediate wow.
Yes.
that turned into a whoa in a hurry.
Yeah. Yeah, whatever voltage you put through that load, it will all be used up, but it won't necessarily be used up in a functional way.
Very good.
Heat and light aren't what we want usually.
Here's a question from John Allen. Manufacturers have been recommending line surge suppressors on newer ModCon boilers. Is this now common recommended practice? I seldom see it.
Line surge protectors. I don't know. What do you guys think?
Rick, you're more the boiler guy. What's your thoughts? And we got Jason and Wheels out there too. What do you guys think? You're muted, Rick.
For a while, it was an issue because voltage spikes and reductions coming from the power grid would, and I'm talking several years ago, had issues with how the boiler would operate. So they kind of wanted that a buffer, so to speak, and that's what that load surge protector would give us. Nowadays, I think most boiler manufacturers have something built in. So it kind of knows what's coming in, and if it gets too high, it kind of cuts it off, or if it gets low, it tries to buffer it up. But again, I've been out of that business for a few years, so I'll let others comment, and we'll look at the questions coming in.
Yeah, again, Jason or Wheels out there, if you've got some input on that, that would be helpful.
I kind of think it's a problem mostly from the past, except maybe in rural areas. Like Colorado mountains, I think we still have some of that where the voltage can really depend on what rural electric sends you and what else is going on. Somebody else?
Dog was barking outside, so I had to close the window.
Oh, I thought you said Doug. I thought Doug was barking. Who's Doug?
Doug was barking outside? No. Jason Mango says yes. Okay, in regards to the
Cool.
power. All righty. Let's see. We got a lot of questions coming in. When did HVAC manufacturers start making the unswitched side of the 24-volt transformer connected to the frame of the equipment? That's from Roger Brandstatter. I'm not quite sure what you mean there, Roger. HVAC start making the unswitched side of the 24-volt transformer connected to the frame of the equipment.
Okay, so I want to take a stab at that. Might not understand the question right. That seems like that would be a design element of the equipment manufacturer. The switch side of a transformer. Oh, geez. Okay, we're talking the primary side where electricity comes from the grid into the transformer. We're not talking about the side of the transformer, the secondary, where electricity goes out. So the side where electricity comes in, you want to have the power side, L1, switched. You always want to have that side switched. The other side is neutral. And so that could be grounded, I guess, to the equipment. The risky part of that is you don't know for sure, unless you ground the equipment for sure, that it's grounded.
And if it's not grounded, it can be dangerous.
Well, it means you have electricity going wherever it wants to go, and you may meet it somewhere by surprise.
This is rarely a good thing. All right. Mike, I see your question. We're going to get to that in just a second, but I want to say it's more for Carol here. Can we explain how electric hot water tank works? How an electric hot water tank works. That's one we'll have to take. We'll have to take it. We run voltage through an element. The element gets hot. The water gets hot as a result of the element. I think that's kind of it. That's the simple version. That's a simple version.
The simple part. Let's do power supply switch and load on that. So power supply is what, your 120 from, yep, the panel. And the switch is your thermostat or your thermostat controller, where you have the water temperature set for. And so that's going to be your open or close switch. When the water temperature drops below that setting, it's going to close the switch. When you close the switch, electricity goes to the heating element and it makes heat until that switch sensor senses that the water is above the temperature its set point, and then it opens the switch and the electricity quits flowing through the switch and the element stops working.
Hey, Skake, let me know if that answered your question, Miley. Jordan asks,
There's another piece of that. I'm on a roll.
Oh, okay. Go ahead.
A water heater has a limit. In the old Honeywell language, probably current even, it'd be like an L4064, a controller. No, that's a four-steer thing. What would it be? L4006, an aquastat. And so the aquastat is going to let the water, going to take it up to a certain high level that's in the aquastat setting, and then it will let the temperature of that water drift down. Talk about the water in the tank, maybe 10, 12, 13 degrees. That's called the differential. The aquastat's going to have a setting for that too. And that's how cold the water can get before you bring on the heat again. That keeps the heating from going on, off, and up a degree, down a degree. Nuh-uh. We're going to have a whole lot of degrees. And that explains why sometimes your shower's hotter than other times.
A little high limit, low limit kind of thing, plus the differential. There you go.
Yes.
All righty. Is there a strategy to prove a control board is faulty that is having intermittent performance issues? Plumber's law being that the homeowner claims the boiler doesn't work, but once you show up, everything is fine. The cycle continues. Oh, Jordan, yes, that's the life story of all of us.
That's the answer to that question. Yeah. Yes, I'm sure there is. I think it's just don't show up.
Not sure that's a good long-term solution.
Then call somebody else. Intermittents are hell. Just hell. Yeah.
Yeah, that's Dave, Rick, how did you guys handle that sort of a situation? Because you got to try to, my experience, you got to try to recreate what the problem is as best you can.
Yeah, ask enough questions, try to get them to duplicate the situation when they normally have the problem, and hopefully it works for you.
Yeah, hopefully you get enough questions answered while you're there, but so you don't have to come back again. But yeah, they may have to. Yeah, always try to recreate it. Every house is different. Every time I walk into a house and just listening to the different noises and what's going on, and whether or not that's the proper noise of the house, or is it just funky while you're there? So yeah, it's a tough one.
I can remember doing a boiler replacement many years ago. During the rest of the house was going under a minor rehab, but we replaced the boiler, and customer was just not happy. They kept saying, boiler's not working. We're not getting heat. At least on the first floor. Second floor is okay, but we're not getting heat in the first floor. All right, I'll be there in the morning. Show up in the morning, they're getting heat in the first floor. And says, yeah, I can't make it do, I've tried a bunch of different things. I can't make it not do what it was not doing last night or when you called me. And I don't know what to tell you. He says, well, okay, I guess it's working fine. Same thing next day, same problem. Boiler's not working. Upstairs is fine. First floor isn't working. Something's crazy going on here. I don't know what it is. And they started getting really mad. And every time we went back, we could not make the problem happen again. It would only happen, and this is when, okay, after 6 or 7 visits, it's finally time to ask a few questions, duh, you know. What time does this happen? And I says, it's usually, you know, between 5 and about 7:30, 8 o'clock, I got nothing. Then, you know, sometimes after 8 o'clock, I have to go to bed, it works okay, but it's at 5 to 7, 5 to 8 o'clock problem. I said, huh. And nothing changed. Nothing else changed. I said, no, nothing else changed. So I'm poking around and I go in the kitchen and I see the oven, okay, the stove or the oven. Then I go into the family room. On the other side of the oven is a thermostat that wasn't there before. The thermostat was on the other wall before, but they moved it to this wall because that's where they wanted to see it, on the other side of the oven. And the oven would get hot when they'd make dinner. No heat.
Sure.
Yeah, that consumed about 2 weeks of my life.
Go figure.
Yes.
Yeah.
Or a lamp or a television back when they created heat.
Mm-hmm.
Yeah, I you know, to do that troubleshooting is start simple. Start disconnecting the simple stuff, right? So if we were looking at a relay controller or a zone valve controller, I'm eliminating the thermostats and using my STSs all the time. My
What's an
sophisticated thermostat simulator, a jumper wire.
Oh,
Oh, you mean an automatic electronic call for heat simulator?
Correct, right.
There you go.
So I start simple there, and just to make sure it's not going to be a wire in between, or it's not the thermostat issues like that there, and you know,
Yeah.
and try to recreate it that way. So yeah, that's the way I start with the simple stuff, and disconnect and finally get down to the control board. You know, is it the circuitry on the control board, something happened there that's giving the intermittent issues? Now you've got it all isolated. So try to isolate as much as you can and verify the parts and pieces that have worked along the lines, and then you can minimize which control you're looking at.
Very good. Oh, here's one for you, Carol. Mark Sheen's not giving up. Really wondering how loads in series work when the first one always eats up all the electricity.
Loads in series. We do not want to put loads in series. Period.
He's referring to Christmas tree lights again.
Right, they're designed to be in series, but in our business in HVAC, loads are just not put in series because they don't behave right. So let's say you have let's do light bulbs. Let's say you have a 25-watt light bulb and you have a 60-watt light bulb wired in series. That means the electricity has to get through both of those bulbs and back to the power supply before either of them can light. It doesn't matter which of them is first. I have a little demo board we do when we have a live class. We have a 25-watt bulb and a 60-watt bulb, and turn it on. And what it looks like is that the 60-watt bulb is off, completely off, and the 25-watt bulb is completely on. And so then they go, oh, well, the electricity goes to the first one. I'm going to switch these around. It's the same when you switch them around. The 25-watt bulb appears to be on and the 60-watt bulb appears to be off. And when you think about the electricity has to go through everything in the circuit and get back to power supply before anything will work. So you put your hand around the 60-watt bulb. Yes, there's some heat there and a little bit of light. The principle that's going on here is electricity, like teenagers and employees, take the path of least resistance. The The electricity can go through the 25-watt bulb much easier than it can go through the 60, so that's where most of it will go. And then just like in the kitchen at your shop or in the kitchen at home, somebody has to do the dirty work. So a little of the electricity needs to go through the hard path, the 60-watt bulb, or nothing will get done.
There you go.
And
I love
that's
your
why we don't.
analogies.
You want to talk about dogs? We can talk about dogs.
We can talk about dogs. All right, power surges will kill sensitive controls. We always use aftermarket surge protector, says Kiefer. And it's not a surge protector, it's a power regulator, says George Conrad. What else we got here? Okay, NEC requires a manual reset on electric water heaters that breaks both legs. Okay. A lot of comments here. Resistance spec through board. Don't really see that. I'm not quite sure what that question is. Mark Sheen, if you want to rewrite that one, I'm not quite sure where you're getting there. Let's see what else we have here. Boy, lots of comments coming in.
Oh, everybody woke up.
Yeah, there we go. By an electric hot water tank, the element is getting it from both sides, 102 volts. So how come when it works, is it not tripping? How come when it works, it is not tripping the breaker? An electric water heater, the element is getting it from both sides, 120 volts. So how come when it works, it is not tripping the breaker?
It's 240 volts if you're getting it from both sides.
Okay, again, I'm not entirely following the question, but you want to handle that one, right?
And the breaker, it needs to be a breaker, circuit breaker that's designed for that voltage.
Gotcha. Well, that makes sense.
Most electric water heaters are 240 volt. Yeah, we're not looking at 120. The only 120s you're finding are little tiny ones you're putting underneath the sink. So
right, the plug-in ones or whatever. Yeah. Yep. Okay, gotcha. All right, that makes sense.
So that's why it doesn't trip the breaker. When you see 120, that's add that up.
Ding, ding, ding.
I think John can do the math there, right?
Give me time. Hey, Carol, I got a question for you. How could I buy all these wonderful books that you have here?
Well, you could go to the website, and I have a bundle price for all 4 books of $39. It's the bundle.
$39 for all 4 of those books?
Yes, they used to be priced at $20 each, but because of COVID and all that, everybody quit learning, man. So we put a bundle on it, and it's a hell of a deal.
Excellent.
A house wiring book isn't about how to wire a house. It is about, special for people in our industry, how to think about how a house is wired using our kind of thinking, which is power supply, switch, and load. And yeah, and by the way, in the back, it does tell you how to wire a 4-way switch and a 3-way switch, just as a bonus.
Oh, very cool. Very cool. So $39 for 4 books.
Yeah.
I'm doing the math here. That's less than $10 a book.
I know. I'm not getting paid very much.
$10 a book, but less than $10 a book.
And I pay the shipping. Do I know? $3.95 for shipping.
$3.95 for shipping. Do you ship to Canada?
Yeah.
We have a gentleman. I guess you're from Quebec.
No. When somebody from Canada orders, I send an email back says, nah, you're gonna have to pay more.
Oh.
Shipping to Canada is crazy.
Yeah, it is. It's not easy getting stuff across that border.
Well, there's
maybe
that
if you
too.
stand on one side of the wall, we'll catapult a package over for you, Dennis. That might work.
Let's play medieval time. Catapult it over. Yeah.
Oh, Matt Cassidy's not happy either. You don't ship to the Great White North. Come on, eh?
Oh, I'll ship. I just charge more.
Oh, he'll ship. She'll ship. She'll just charge more. That's all. There you go.
Anything for a price. You know that.
There you go. Anything for a price. All right. Well, listen, and here's another question that came in. Are you related at all to Tina?
Oh yeah, she's my twin sister. Different mothers, twin.
Twin sisters from a different mother. There you go.
Yeah, you remember that. She's also a lot younger than I am, I think. But yeah, we're related.
Okay. This is my younger twin sister from a different mother.
Yes, from a different mother.
That'll get somebody
And
to
different
think.
father.
That'll definitely get somebody to thinking. All right. Again, we're going to open this up. Any questions at all now? It's we've gotten a lot of great information from Carol. Thank you so much. And any more questions you guys have about electricity in our world, or we'll open it up to any kind of a discussion that you all want to have. Oh, wait a minute, Dave.
Yes,
Dave.
sir.
Dave.
I'm waiting
Are
for you.
Ready, Dave? We've got to go and figure out who our winner is from last week, and we have to give the win. We have to pick a winner for this
Yes.
week.
You
So
have a
I'm
lot
taking
more
the
to
screen
do.
back from you, Carol.
Okay.
All righty. And we'll go up here. All right. The trivia answer for this week, and as of 8:20 p.m., no more answers are welcome. Of course, everybody got this one right. The shark's name was Bruce. The big old mechanical shark's name was Bruce. All right, and we are going to need a bigger boat for next week. I'll tell you that. All right, we're going to need a bigger boat. Next week, we'll be talking about ModCon piping and pumping, and we're going to talk a little bit about ECM circulators, the real story, as we wind down the summer session. Looking at 2 more sessions, I think, for this summer, and then we'll be getting our fall stuff ready for you guys, which I think you will enjoy. So that's going to be next week. I'm going to turn it over to Dave because we have to figure out who is the winner of last week's trivia contest. So I'm going to make Hooper the presenter. All right, you take it away from Quint. And Carol, farewell and adieu, you fair Spanish lady. Thank you so much.
Oh, thank you so much. Always fun.
But don't disappear yet. So we'll let you know when we're going to kick out of here still. So, so last week, the trivia question that you had out there was the director, George Roy Hill. What 2 movies did he do with Paul Newman?
Yeah, Beyond Slapshot, because last week was Slapshot, was the movie of the week.
Last week, yep.
What other
Beyond
2
Slapshot.
movies?
Yep, was Butch Cassidy and The Sting.
Right.
Was the answer to that. So yes, I think I'd like to review what we did last week. So we had quite a few answers, as you can tell by the list of names here. So let's click on that and let's see who our winner is. So I sent out some packages earlier this week for those of you in the past, and let's see, is it going to end on Jeff? And it ends on Jeffy.
Hey!
Jeffy. So I will be sending out a prize package.
Even Lola's impressed.
So I got a whole bunch of things in the bag, and those of you that are on Instagram, you probably would have seen some of those pictures of stuff that I sent out this week. So Jeffy, good job. Thank you. Thanks to everybody that also puts in answers.
Amazing.
Yeah.
The stuff you spinner. Wow.
Oh yeah. Now we had some good stuff in that prize package. We had what did we have? We had the new Takeo mask, which everybody's got to have one. We had a couple of screwdrivers. You had a pocket knife. What else?
I did. I've got a beer can koozie and a bottle koozie. I also have a Bluetooth speaker, portable Bluetooth speaker that went in there. A couple of hats. I've got the real tree hat, and I got a straight black hat, and the coffee mug travel coffee mug that we always leave sitting on top of the water heaters on every job site. So, yeah.
And Jeff wants to know, how are we going to get it across the border? Because he too is Canadian.
Carefully.
It's gotta cost you about $50 at least.
Yeah, I'll take a drive up to you, Jeff.
There you go. No, they're not letting us in.
No.
Well, we'll just stand on either side of the line, and I'll just hand it over to you.
There you go. No, put it in a barrel and send it over Niagara Falls. There you go. He can catch it he'll be on the Maid of the Mist. He'll pick it up down below.
You're nuts. Completely nuts.
Hey, I'm not nuts. He's the one going over the falls. It's not me.
Right.
Okay, he's nuts.
If you knew Jeff, you'd know.
Okay.
We love you, Jeff. We love you. We love you like a brother. Who is a new granddad, by the way, first time grandpa. So congratulations,
Oh,
Mr.
congratulations.
House. There's another house in the house, so to speak. And yeah, we got and then what else do we have? There was all that. That's a pretty cool prize package. And again, the masks are just all the cool people are wearing them. All right, the Takeo mask. Just important to know. Every cool person I know is wearing a Takeo mask. And
You
I
know what
know a
you can
lot of
show
cool
me
people.
right now? Oh, I was
Oh,
hoping there was.
Hold on,
Look
hold
at that.
on.
Yeah, Rick has it. Rick has it. Put it on, Rick. He's going to do it.
It
Looks
makes my
good.
ears stick out.
Also
Just-
makes
just-
your face look black.
Hides my.
Scary.
Here we go. And where is the, there it is, there, no, other side. There it is, right there.
No
There's the
COVID
little
here.
Takeo. Nope. Now, if it was really cool, it would be put like a big 0015 or something right across the front. Now that would just be neat looking, you know? With teeth.
Let's see if I can. I want to screen share something here.
You like
I
that?
can-
You know, have that right in the middle.
There you go.
John,
I like it.
John, I want
Oh,
to
you
show
want-
you a map. Let me share my screen.
All right, I'm going to send it back to you, Carol. Oh my.
Now, there's a mask.
That's kind of frightening.
I like it.
That's my homeless buddy, Jack.
Wild and free.
Gotta
Oh,
love it.
boy. Yeah,
Gotta love it.
okay. I'm taking that down.
One thing I've learned is that the iPhone's face recognition doesn't work when you're wearing a mask.
Well, duh.
Yeah, well. And a friend of mine posted on Facebook today that she saw 4 men walking into a bank and none of them were wearing masks. And she was very upset. And I had to tell her, well, at least we know they're not holding the place up.
Oh, yeah.
Yeah, that's the upside. But the downside is everybody should be wearing a mask.
Yeah, could you get shot for walking into a bank with a mask? I think they
Yeah,
would be
used to
confused.
be. Yeah, used to be.
That would be the last thing you want to do.
All right. How can I get my hands on a few of those? They are awesome. Now, Kiefer, just send a little request our way. We may be able to do a little something. I'll wash this and give you this one. No, I'll keep this one. I wouldn't send out a used mask. That would be that'd be very low class. And even for me, that would be low class. So I wouldn't do that. Didn't see Butch and Sundance wearing those in the movie. No, they never wore masks. Well, Butch and you put a mask on Robert Redford and Paul Newman circa 1969. Of course you wouldn't. You know, they're good looking men. That'd be like putting a mask on Dave and I if we were going to hold up a bank. We wouldn't do that, right? Well, never mind. Maybe we're a bad example.
We don't know what you would do.
There you go. Adam Popkin, send us a note. We'll see what we can do for you. That's all. That's great. That's great. Way to go, Sherlock. Okay, yes. Where do you get Takeo mask? Again, we've got some promo ones. So both Dave and I have some. So just again, send us a note, an email or something, and drop us a line. We'll see. We'll send them out till we got none left. How's that?
Where'd you get those made?
The magic goodie man at Cranston made them up and sent them out to us. I don't know where he got them, but that'd be our marketing team that came up with
Yeah, I
these
think
things.
we got it from our normal place that we got our shirts and all from. They also started getting involved in the mask craze.
A whole new product line. Who'd have thought?
Oh, hey, look at this. I just got a text from Jeff House with his grandson.
Hey.
Oh,
Excellent.
That's-
Glad he's doing great, brother.
that's the new house in the house. That's awesome news. And that, good for you. That's very exciting. That's very exciting. Good to have him. Oh, here's a big one from Jordan. Okay, let's see.
Well, I got a simple question from Mike Hansen that asked a little while ago, and he was just wondering if he can get a simple explanation of ZC and versus ZR on a switching relay.
ZC.
Yeah, ZC and ZR, other than Z center and Z right. So,
Okay, so you don't want the simple one then, don't
not
you?
that simple, I don't think.
Yeah.
Yes.
Well, I guess, and I'm going to give you about as simple as I can make it. One is 120 volt Gazauta, and the other one's 120 volt Gazinta. If you go to one of our multi-pump relays, there's a jumper between ZR and ZC, right? And internally, power comes out of ZR and goes into ZC, or it might be the other way around. I can't remember which one's which, but power goes out of one. We put the jumper, goes into the other to energize the relay. Normal operation, just leave that jumper there. There's no reason to take it off. The only reason it exists is for, let me take this thing off. I don't have to socially distance. No one's within 100 miles of me. The only reason that it's there is for boilers that have a tankless coil. And internally on the boiler control, there's a ZR and a ZC. So to get this relay to work with that control, all right, which is admittedly very old school stuff, you're not going to find them out much outside of the Northeast, is ZC from the, what you would do then is you take the jumper off of the relay, then you would wire ZC from the relay to ZR in the boiler control, and then ZR from the boiler control into ZC in the relay, or ZC to Z. You'd complete the circuit. And that's basically how that control has to work with that boiler. The internal stuff, they'd have to go rip it apart and take a good look at it. But that may be the simplest version I can come up with, and that's simple like radar right now. Unless you are using a tankless coil, there's really no reason to take that jumper off. There might be some instances where you might want to play around with it to do a couple of different interesting things. And we can show you some of those. Maybe that's good. That's good for our final session for part 7. We'll get into some of the controls and some of the interesting things you can do with them. I think maybe we'll share with you some of that stuff. But that for right now is about as simple as I can make it. Maybe that's not that simple, but unless you have a boiler with a tankless coil, there's no reason to do anything at all with ZR and ZC. Does that fit, Dave?
That works.
All right.
Works for me.
Did that help at all? I'm not sure if it did or not, but that's it's a Gazinta and a Gazauta. That's all I can tell you.
Mm-hmm, mm-hmm.
If you connect the Gazauta to the Gazinta, life is good. Life is good. All righty. Now we got a long one here from Jordan. Let's jump into this one here. Nope. Got to put this back on. Looking to create the following control strategy for domestic hot water recirculation, looking for ideas to accomplish this. For a controllable time frame, 6 to 8 a.m. as an example, I'd like to be able to have a tankless turn on for 5 minutes every 30 minutes for that time frame. After that, it either doesn't turn on until the evening, or I could reduce how often that unit turns on during the day. Essentially, a very custom electric timer. Wondering if anyone has tried this, looking to take the Takeo Genie and the smart plug to the next level. Okay.
Okay.
If I'm understanding you, Jordan, you want domestic hot water recirculation on a timer based on a timer for a tankless. And I'm guessing
customized. It doesn't have to be tankless. He's looking for tankless because just to get the, but it doesn't have to be for a tankless. But
yeah,
he's looking for a smart plug.
Yeah,
but customizable too, where the smart plug is not just learning the events going on. He wants to control the events, but then make it a little more customizable too. So, the only thing that you could probably consider doing is getting yourself a a Wi-Fi plug-in switch. You know, like Wemo make a few of the companies out there, and you can create your own custom scheduling on there, and they call it if this then that. So you can, there's a whole bunch of different websites out there to learn about that, and you can create custom programming in that respect. I have a little light, I have one used for the lights down here in my home office. And all I do, if you've noticed once in a while and during some of the takeaway after darks, when they run on for a long time, all of a sudden it gets dark down here, the lights go out. So I programmed it so if I turn it on, the lights turn off 2.5 hours later, to make sure I don't forget to turn them off, because it's just an old halogen torchlight lamp. So when I started working from home more often, I would walk down here in the morning and see that I left that 500-watt light on the entire night. So so that's what I did, so I wouldn't forget to turn the lights off in that area. So there's ways to do it. If you need some help,
Very good.
shoot me an email, Jordan.
There you go. And if you're looking at, if it's a tankless, tankless in general, you don't want to run a tankless on a timer anyway, because unless it's drawing water, you're just going to short cycle the crap out of that thing, and that's just going to put it into an early grave. What I've seen people do, which kind of defeats the purpose of a tankless, but it kind of helps in terms of if they want a timer-based recirc, is just have a storage tank. And the tankless maintains the temperature in the storage tank on some sort of on an aquastat, and then you can recirc off of the storage tank. Again, it kind of defeats the purpose of having a tankless, meaning I'm not trying to keep a big old tank of water heated up to a certain temperature, but it eliminates the timer control on a recirc pump that's going to cause the tankless to short cycle like crazy. So, recirc with a tankless can be done badly, very easily. And, like I said, a timer and a tankless just doesn't work great. Otherwise, it's on demand. But I can see what you want to do. You want a combination of on demand and timer for that tankless, so the tankless is ready to go, and you don't have to wait a couple of seconds for the tank to get flow through the tankless and then get the tankless up to temperature. One of the things about the Genie is, if you press that, with the manual enable, you can press that button before you need hot water. You can press that button, let the thing run, let it take its 20, 30 seconds before the hot water gets there, or however long it would take before the hot water gets there, and then jump into the shower, and then turn the shower on and get in the shower. Like, I know guys that'll, first thing, one of the first ones I ever saw is a guy put the push button next to his bed. All right, when he got up in the morning, he pressed the button to enable the Genie to get the hot water going. So by the time he got up, put on his robe, waddled over to the bathroom, did what he had to do, then turned on the shower, and he was good. It's just a matter of when that sequence starts. Now, there's a lot more, maybe a lot more interaction or personal contact or personal involvement than someone may want to have. That's when you have that's when the motion detector comes in. And then where do you put the motion detector? Could that be in the bedroom? Could that be on the entryway coming in to the bathroom? There's all kinds of different questions. But yeah, it's the tankless and recirc is always a challenge. It's always a challenge. Is that right? What else we got here, Davey?
Haven't seen too much else out now.
I got one for Carol.
All righty.
Say, Carol, nowadays, some of our circulators, especially some of our new ones, like we introduced the 0034E series, and it kind of knows what voltage you're going to give it. It's got 3 wires, okay? And you can run 240 or you can run 120 to it. What is it using internally to make a decision? Does it just have some kind of little ability to sense what the voltage is and then send it, both legs? If it doesn't have enough, then it just sends the one leg. I don't know if you know that, but that's something that's going to come up. And I've got a follow-up to that after you answer that.
Oh boy. Does your follow-up depend on what my answer is?
No, it's something else.
Does my initial guess is it's like a multi-tap transformer in that you can, the multi-tap transformer in the primary, you can put almost any voltage into it. You have to pick the right wire. You have the common and then you have the other one. And then the transformer has windings to deal with each of those to reduce it all down to what the controller is really looking for, which let's say it's, if you put in 220 in the primary, it will reduce it down to 24 volts. If you put in 120, it reduces it down to 24 volts. If you put in 110, it reduces it to 24 volts. So the control only sees 24 volts. Does that fit with what you're asking?
Yeah, I mean, there's something in there and we haven't dove into it yet. The other side of that, like for instance, we have a 1915E circulator. It's a light commercial circulator that's got an ECM installed on it, but it's similar to the traditional AC motors, big, you know, pretty good sized pump. Got a troubleshooting call a while back that the unit just wasn't performing like it was supposed to. You know, they're looking at the discharge pressure and the suction and saying, man, this thing is just not doing anything. And of course, we all scratched our head and wondered, did you try this? Did you try this? And then it's like, well, pull out your multi-tester and tell me what you got to ground on each of those legs. And sure enough, they run 115 to it, and it's a 230-volt pump. And so the pump will run, but it just won't do anything. So anyway, that goes
Says,
along
I'm
with
so hungry, you are starving me.
yeah.
There you go. Here's a question from Jordan again, a follow-up. Can the Takeo Genie be connected to multiple motion sensors? And has anyone had success connecting them wirelessly? Example, having one in the master bath and one in the kitchen. Yes, you can have multiple wireless sensors. I'm not entirely sure there's even a limit. I think you can have push buttons. You can have the wire. We have a wireless push button as well, like a garage door opener, kind of a clicker. And then we have the wireless, and then we have the motion sensors, and you can put as many of those in as necessary.
Right. So each of those is a switch. It functions as a switch, and you can put as many switches on any load that you want to.
There you go. And as far as wireless, they're all wired. As far as wireless motion sensors, we've looked at a lot of different ones, and the challenge is getting one that's reliable. It's going to work in a lot of weird applications, because we may find that it works in 6 out of 10 or 7 out of 10. It's those 3 out of 10 that just raise nothing but holy hell for you. So we've been looking at a lot of different ways of doing that, and we haven't stopped looking, but we don't have anything that's going to come out imminently. But yeah, many of those as you want.
Hey, John.
Yo.
I've got a wiring diagram specifically for the Genie, and there are some limitations. And if you give me the screen, I will show them to the folks.
You got it. There you go. You are the dude.
So you got it, or do I have to click on something, right? Show my screen.
Yep. You should get. It's there. You go. You are rocking. You are rocking.
Okay, as you can see, of course, I got all this stuff in the way now. I can't even see my own screen, but let's do this. Okay, so we can do the push buttons. You know, we put a bunch of those in line. That's one separate wire there. If we're doing the wireless remote transmitter buttons, not to exceed 10 per receiver. Okay, so there's a slight limitation on that as well. Let's look at another configuration. If I have motionless sensors, I can't exceed 10 on those as well. I could do the wired push buttons, but then I got a limitation. And then thirdly, on the last page, I can do momentary contact buttons that are wired. I can do wireless sensors along with the motion sensors along with the wireless. Again, 10 is the number here on the multiple wireless transmitters, and 6 is the limit on the motion sensors. So. All right.
Very good. Excellent. Anthony Ryko says he'd like to get that slide.
This is a PDF. Anthony, send me an email. I'll be glad to share it with anybody who wants it.
There you go. Excellent. And then your email address, Rick?
It's RICMAYMOUSC. Okay.
I knew that was coming. RICMAY at
Takeo.
TakeoComfort.com. Yes, we're gonna get back to calling you the Lorax now, Rick.
But, yeah.
Yeah, I like the
Lorax at takeohvac.com. Yes.
Oh,
Thank
I
you,
like
Steve.
that. Yeah, maybe we'll check with HR, see if they'll change your email to the Lorax.
Cool.
He hangs out every night. Every night
Yep.
we're down here.
Show
Lorax.
Carol, you gotta see Rick the Lorax.
Okay,
It has to do with a shirt I was wearing one night, I think. And I think it was Wheels that actually pointed it out. So
Yeah.
looks like you.
Thanks. Yeah. The Lorax is a good person.
He is. Unless someone like you cares an awful lot, nothing's going to change. It's not. That may be the quote of the century right there from the Good Doctor and the Lorax. And I learned that. I remember watching and reading the Lorax as a kid and watching the cartoon, but Jeff House actually used it in a training session, and it kind of hit me like a ton of bricks. And I've stolen it from Jeff and claimed it as my own at this point, but that's what I do. So,
Too bad.
but that is the Lorax, and that is you, Mr. Mayo.
Okay.
All righty, guys. Any more questions coming up? I mean, we've been at this, boy, again. Yeah, it's almost a 8:45 here on the East Coast, and was it be 5:45, 6:45 where you guys are, right? Out in the Midwest, out in the mountains.
Mountains, yes.
Very good. You guys had dinner yet?
Not yet.
No.
Well, you must be hungry.
Well, I'm going to have dinner pretty soon, but
There you go.
I'm
Oh,
not
here's a
sure.
20
Here's a
volts.
question. Oh, sorry, here's a question from Mike Hansen. I've been getting questions about why no ground on the ECM residential circulators. What is a good explanation, gentlemen?
Well, it's not all of them. It just happens to be our 44 watt version of them because
Right.
it has to do with the manufacturing process. And what we end up doing is doing an injection mold around the windings. So there is no way for stray voltage to actually get through, so to speak, all that plastic, vinyl plastic that we have around the motor itself. So we have that injection mold. Everything is embedded right in there. So that's where you're going to see most of the juice.
All right, so good. No ground wires needed. So we've simplified your wiring by 33% with our 44 watt circulators.
Another good analogy is, of course, a lot of the Milwaukee tools are all battery operated now. But for instance, if I walked out to my garage and grabbed my Milwaukee Sawzall, it doesn't have a ground because it's double insulated.
Right.
Same thing.
Yep.
There you go. Hope that helps you, Mike.
Yeah, I mean,
Very
some
good.
of our other circulators, BT2218, and some of the other larger 34E, larger ECM circulators do have a ground wire. So it's just the small one does. Yeah, does not.
Very good. Is there an app to control and view pumps in use coming in Taco's future? That's Jordan. Is there an app to control and view pumps like the 0018E ECM circulator and its Bluetooth connection? Yes, well, we do have a Bluetooth circulator that can connect to an app, and we can control and program that circulator about as well as a circulator can be programmed.
Other than turning it on and off. Yeah, just can't turn it on.
Other than turning it on and off. There you go. And it gives you a whole array of different operating modes, and that's the 0018E variable speed circulator. Is that going to go into new? And we were the first ones to come out with a Bluetooth circulator in North America, and for residential purposes. Will we be seeing that technology in other circulators? Most definitely, but it's a matter of when and in which ones. That remains a product development question, and they don't check with us. But yeah, that's in existence already in the 0018E. And Dave, you were raising your hand. Was that? Oh, your lights just went out.
The lights just went out. Yeah.
There you go.
I'm not going to bother turning them back on. So I get enough light off the screen here.
Very good. Here's a question. How do you size pumps for a mix of 50-50 glycol and water? Well, that's a good question. You got to be, there's your basic pump sizing is you got to find the flow, right? You got to find your flow rate. And to find the flow rate, we typically use GPM equals BTUH divided by delta T times 500. The GPM is your gallons per minute flow rate. BTUH is the heating load. Delta T is your design for temperature drop across the pump, the heating circuit. Typically 20. For residential rating, it might be 10. For snow melting, it might be 30. For indirects, it might be 30. And then 500 is a constant that is derived from multiplying the weight of 1 gallon of water, 8.33 pounds. We used that already tonight, times the number of minutes in an hour, times the specific gravity of the fluid. Water has a specific gravity of 1, times the specific heat of the fluid. Water has a specific heat of 1. 1 BTU to raise 1 pound of water, 1 degree Fahrenheit, 1 hour, blah, blah, blah. So 8.33 times 60 times 1 times 1 is 499.8. We'll call it 500. So we use that formula to figure flow. Now, the more glycol you put in, that 500 number gets lower, all right? What you need to do, and this is the short version, Roger, is you got to figure out what glycol am I using and what is the denominator. I got to find out the specific gravity and the specific heat of the percentage of glycol that I'm using. So I got to figure 50% glycol, 50% water. What's the number? What winds up being the denominator? What takes the place of the 500? Is it 430? Is it 435? Is it 450? It's going to depend upon the fluid, and it depends on the mix and depends on the brand that you're using. Once you do that, then you can do the math. You'll find that your flow rate is going to be higher than it would be with straight water, obviously, because 30 times 500 is 15,000. 30 times 400 is less. Okay, it's going to be less. So your required flow rate is going to be a lot higher. That in turn is going to create more head loss through the piping circuit. So you got to figure out what the head loss through that piping circuit is at the higher flow rate, at the temperature of the fluid that you're running, and then that's when you get your flow and head, and then it's simply the same thing you've been doing. That might be another session we can do, because I've got actually a presentation on how to do just that. So we can do that again. We can do that as well in the future, to figure out doing 30% glycol mix, 50% glycol mix. And the thing about glycols, and I think Rick and Dave can verify this, is they're not all the same. Depending on who makes it, you're going to get different numbers and different values, and there's no industry standard. So I can't just say all glycol 50%, it's going to be this number. It depends on which one you use, okay, which brand you use, what color it is, and all that crazy stuff. And they make them to work to different temperatures too. So there's a lot of different stuff in there. So I'm hopeful that again, another non-answer answer. I guess I'm good at that tonight. Sorry, Roger, but that's kind of the long and short of how you would do it. That's the mechanics of how you do it. And I think we can do in an upcoming session. We can do a little tutorial on just where do you find the numbers and what do they actually tell us. So that's a great question, Roger. Thanks for asking it. All right. See how this goes, Carol? I mean, just when we think the questions have dried up, well, another shot comes at us.
I gotta pee here pretty soon.
Well, okay then.
Hey,
we can let you go.
you don't have to raise your hand.
Yeah, this is not that formal of a session. If you gotta.
And just remember the most famous thing you have to remember in doing all these webinars: turn the camera off if you're walking away. Yes.
Kind of like turning the microphone off.
Way too many people out there leaving cameras on. Yes.
Yeah,
there you
because
go.
the bottoms may not match the tops. So. There's some good stuff out there about that.
All righty. Okay, any more questions coming in there, folks? What do we have? No, looks like we're kind of dried up. The last call. I'm going to do the last call for questions, and then we'll make it a good night. All right, I think we got them all. Folks, thank you very, very much again for being with us on another edition of TACO After Dark. This is starting to become a Wednesday night thing. I guess we're going to have to keep doing this, till whenever. I guess if you guys get a chance to send us an email.
up. Yeah.
Say what? Until
Till
nobody
nobody
signs
signs
up. There we go. Yeah.
Great.
You guys get an opportunity. Send a note to myself or Dave or Rick about how you like the format, how you like the time. 7 o'clock on 7 o'clock in the East Coast is great. Do we need a West Coast version? If you guys are from out west, if you'd like to do it 7 o'clock Pacific time or something like that. I'll volunteer Rick for that job, right? But this is going to be going on for a while, it certainly seems. So we're going to have to adjust and adapt along with it. So we'd certainly like your input on what you would like. But with that, many, many thousands of thank yous to Carol. Thank you for joining us. We really appreciate it. Wonderful job as always. And Dave and Rick, we'll see you all next week.
Yes, thank you, Carol.
Yeah.
Greatly appreciate it. It was
Thank
a good
you.
time tonight. Yes, and to everybody else, thanks. Good to see you all. And
All right.
we look forward to seeing you next week.
Radio, folks.
Okay.
Have a good one.
Bye-bye.
Bye-bye.